Hello everybody and welcome. Today we're going to get started with collision detection, and we're going to start with circle collision detection. Now, collision detection is one of my favorite things to do in game programming. We're going to now add collision detection to our physics engine, but I'm also going to make this video in such a way that if you want to just see how to do circle collision detection and resolution, I'll make a link in the description so you can go down there and just go right to the collision detection. For the physics engine, though, I'm going to get started with cleaning up some of the code and getting the code ready for circle collision detection and body collision detection, rigid body collision detection in our engine. Also, if you want any of the source code, I've got all the links in the description below, so you can download that anytime. And if you want any of the code for the flat library or to see how it was created, you can visit my channel, and I've got videos, and we went step by step and created the extension library I call the flat library. I've got that highlighted right here. And we're going to use that we use that here in our physics engine to get two-dimensional shapes on the display, to handle keyboard input, and to have a camera into the scene. Okay, so let's go ahead and get started with collision detection. And specifically, right now, we're going to work on the physics engine, or getting it ready to handle collisions. Now, before we do anything else, I noticed in my flat vector I had a misspelling. Down here with the equals function, I actually want this to say equals, not equal. I'm going to change that, and I'm going to tell it to rename that for all instances. Okay, and that looks like it works just fine. Okay, and let's go back into the game class. And what I'm going to do now is actually make a way to move the bodies, the rigid bodies in our simulation. And it's not going to be a realistic, physically realistic way. It's just going to give us the ability to move them from one place to another. So back in the flat body class, I'm just going to make a new function, and we're going to call this move. And it's going to be really simple. I'm just going to pass in a vector, which will be the amount we want it to move. And then we're going to be able to take the position of the body and increment it by that amount. And then I also want one more function that will be move to. And this will just move the position to a new absolute position. So the first one increments the position by this amount. The next one will just actually move the position to that position. All right, now back in the game class, we're only going to handle circle collisions right now. Eventually, we'll move on to the rectangle collisions and also the polygon collisions. But for now, let's just handle circles. And so we have the initialization function here. I'm going to tell it that we want all of the bodies that we're creating to be circles. So I have this this random helper that was allowing us to make either circles or boxes at a random interval. So I'm going to tell it the shape type should be a circle all the time. Now it'll never make boxes. It'll always make circles. And the other thing is, if we run this, okay, we should see all circles now. I want to fill in these circles with colors. So we can actually distinguish them from one another, and actually makes it look a little bit nicer as well. So I'm going to make another array up here, and I'm going to make this an array of colors. And I'm just going to call this colors. And then down here in the initialization function, let's go ahead and change some of this stuff. I'm going to move the body count up here. I'm actually going to pass the body count in as the initial capacity of the body list, so then it'll start with that capacity. We also want to create the colors array, and that's just going to be the same size as the body list. And so I'm just making one color for every body that we have, and it's going to be the same size as the body list. Okay, and then down here, as we loop and create each body, here's where we add the body to the list. I'm also going to add a color to the list. So at the index I, let's add a new color. And I actually have my random helper class has a function that just returns a random color for me. So I can just get random colors and they're ready to go. And of course, if you want to see that code and how I wrote it, it's all in the source code in the description. And then down here, when we're actually drawing, so right now it's only going to draw circles because that's all we have. I want it to now just, the first thing I'm going to do is draw a circle fill. And that'll be at the position and the body radius. The point count for the circle will be 26. And then here, we're just going to pass in the color that we've created earlier. So now what we're doing is, first of all, we're drawing a filled circle, and then at the same location, we're drawing an outline in white. So let's go ahead and see what that turns out to look like. Oh, it would help if I actually put the right variable there. So that'd be the body count. Let's start over. Okay, perfect. All right, so we have a bunch of circles and we have their color filled in. Perfect. Now, the next thing I want to do is I'm going to change some of our creation variables. So right now I've got the radius at 3 meters, and I want to shrink it down to be about a meter for the radius. So the whole diameter of the circle is going to be 2 meters, and so I want the radius to be 1. I'm just shrinking them down a little bit here to be more like real physics objects I might be using in a game. And then when we shrink them down, I also want to zoom the camera in more so I can see them better because they're going to be smaller. And so up here with the camera zoom, I'm going to change this to, I don't know, let's try 24 and just see what that looks like. And then the other thing is I've got the padding set at a constant 10 meters. And when we're zoomed in, if I have a padding of 10 meters, it's going to make it so I don't have very much room to place the objects. I want to make this a percentage of the extents. And so I'm just going to get whatever the right of the camera extents minus the left of the camera extents. So what I'm doing here is I'm just getting the left minus right is going to tell me what is the whole amount that I can see. How many meters can I see from left to right? And actually, I can't make this constant anymore. I'm going to get the whole extents, and then I'm going to multiply that by 5%, which would be 0.05. And so all I'm saying is I want the padding to be 5% of whatever the whole width is. That'll give me the padding, and I'll just put the absolute function here just to make sure we don't get any negative numbers. Okay, and that should put the padding in there. Let's go ahead. We're zoomed in at 24. The circles are now 1 meter radius. Let's just see what they look like. See what we get. Okay, and it almost looks exactly like what we had before, doesn't it? And it kind of makes sense. That's funny. I didn't even mean to do that, but I think I divided the size by 3 because we went from 3 meters to 1 meter as far as the radius goes. And then I also increased the camera zoom by 3 because I went from 8 to 24. Just kind of fun. I didn't actually mean to do that, but this is exactly what we see looks exactly the same because the zoom went in by 3 and the size of the circles went down by 3 by a factor of 3. That's kind of funny. Okay. That's interesting. Okay. So we have all our circles. The next thing I want to do is I want to be able to take one of the circles and I want to be able to move it so I can test our collision detection. So let's go down to our update function, and we're going to add some keyboard input. And I want to be able to move a circle in a direction with a certain speed. So I'm going to create some variables here. So I'm going to have dx, and this is going to be for a direction in the x coordinate. This will be for direction in the y coordinate. And then I also want a speed, which let's just do 20. And the way I'm going to measure this is in meters per second. So do 20, actually at our current zoom, that might be kind of fast. Let's tell it I want to do 8 meters per second. Okay, yeah, that'll be fine. We'll move it 8 meters per second. And then let's check for keyboard input. We'll just use the keyboard class. Again, this is from the flat library. Code available in the description. And let's do, if the key is down, and we want to check for we'll start with the left key. We're just going to do all the arrow keys. If we're going left, that means we want to decrement the x direction. So we're going to take the dx and decrement it by 1. Let's go ahead and copy this. All right. And now let's do all of the keys. So we're going to do the right, up, and then down. Okay, these two are going to be the y. So up and down are going to be the y. Okay, so if we go right, we want to increment the x direction. Going up, we want to increment the y direction, and then if we're going down, we want to decrement the y direction. But the idea is I'm just getting direction. If I have the up and right held down, dx and dy will both be 1. And so then once I have the direction, I want to normalize the direction. So then he'll move at this, or the object will move at the same speed regardless of which keys are held down or which direction we're going. If both the dx and dy are 0, then we don't want to do anything, right? We don't really need, after this point, we don't need to do anything because we're not actually moving. Let's go ahead and check. So if the dx does not equal 0, or if the dy does not equal 0, then we want to actually move the object, okay? So if either one of these is not 0, then let's go ahead and do something here. And I'm going to create a new flat vector, and I'm going to call this the direction. And it'll just take the dx and dy. And then I want to normalize this value because no matter which direction the object is moving, I want it to be the same speed. So I'm going to bring in the flat math library or flat math class, and let's normalize it. And you know what? I've got some conflicts here because I do have a flat math inside my other flat library. So I'm just going to tell it at the top that I'm going to tell it that the flat math is equal to, this is going to be the flat physics flat math. Okay, so now inside this file, what I'm doing is I'm just saying every time I use flat math, I want you to use this reference and not the other one. And so that should clear up all the confusion that the compiler might, or that the program might be having. Okay, so we normalize it. And now I want to get the actual velocity. So velocity has a direction and it has a speed, and they're the combination of that. So I'm going to calculate a flat vector. I'm going to call it velocity. And that's just going to be the direction times the speed. All right, but actually we need one more thing. We need to find out how much time is elapsing between frames, because I want this to happen on a per second basis. So I want this to be in meters per second, and so I need to multiply this. And MonoGame has a game time that they send in the update code, or in the update function. I want to multiply it by the amount of seconds that have elapsed between the frame, and so that way I'll get this unit in a per second basis. I'm just going to tell the game time that I want to get the elapsed game time and then the total seconds. All right. Now this returns a double, and so I need to convert this or cast this to a float, and that should be everything we need. Actually, I have a function that I wrote inside my flat library, and it's called get elapsed time in seconds, and I can just pass in the game time. And this just does the same thing that I did over here. It's just wrapped up in a function. So I'm just going to call that every time I need to do something on a per second basis. I'm just going to call this function and multiply what I'm doing by this function to get the per seconds. Okay, so now we have the velocity. Let's tell it that we want to move the body by that velocity. So I'm going to go to the body list, and I'm just going to take the first one at index 0, and I'm going to move that one, whatever it is. So we're going to move that by the velocity. That should be everything to move. Let's go ahead and run this code and see what happens. Okay, there we are. So I am able to move this. It's moving at a rate of, let's see, what did we tell it? 8. Okay, 8 meters per second. It doesn't intersect with anybody yet, but we are going to handle that very shortly. Okay, so let's get started with the actual collision detection and resolution code. First thing I'm going to do is, in my project, I'm going to add a new class. And I'm going to call this collisions. And this is going to be a static class. So I can just call the functions directly. And as far as I know, my plan is to make all the collisions using the separating axis theorem. We're going to go through and implement it step by step as well. Now, circle collision is kind of unique. We are going to use a separating axis theorem for that, but for circles, it's really simple. There's only one axis to test. Circles are really nice because they're simple and they're fast and they're very efficient. So it's a good way to get started, and then we'll move on to other things like polygons and the rectangles we're doing as well. Okay, so let's go ahead and implement this function. We're going to return a Boolean value, and the Boolean will say, okay, if this is true, they have intersected. If not, they are not intersecting. And I'm going to call this intersect circles. We're going to pass in a vector that has the center of circle, the first circle. So I'm going to call this center A. And then we want a floating point that indicates the radius. So that'd be the radius A. And then same thing for B. Okay, so we have the center and radius of both circles. Now we want to return some value. So if they are intersecting, we're going to pass out some results. Okay, so I'm going to have a vector that indicates the normal of the collision, and then also a floating point value which indicates the depth of the collision. I move this down so we can see it a little easier. Okay, that looks good. And let's talk about what this normal and depth value is. So if there is no intersection, this normal and depth, this normal value and this depth value will mean nothing because there is no intersection. We don't need to do anything with it. But if there is an intersection, we want to get the normal of the collision and then the depth of the collision. So for circles, let me just quickly draw something here. If this is A and this is B, so you can see they're intersecting right here. What we want, here's the center of this one and the center of this one. We want the normal of the collision, which basically tells us, so the normal would look something like this. And basically tells us which direction do we need to move one of these circles, in this case B, to be out of the collision. And what we're doing is we're just trying to push the circles apart. So we find overlap or intersection, and then we push them apart. And the normal tells us which direction do we need to move. Okay, and then the depth tells us how far do we need to move in that direction, which would be this right here. In this case, we would have to move this amount to be out of intersection. So we're going to get those two values. Let's go back to the code and just talk about how we're going to do that. So first, let's detect the collision. So in order to detect collisions between circles, the first thing we need to do is determine how far apart the circle centers are. So let's just get the distance. And our flat math library has a distance formula. We're going to pass in the center of A and then the center of B. And then I also want the radii added together. So I'm just going to add the radius of both circles. And so that's the total radii. And all we're trying to do is now determine if the distance between the circles is less than both of these, the radiuses or the radii of the circles added together, then we have intersection. So let's go ahead and write what that looks like. So if the distance is less than the radii, or actually what we want to do, if the distance is greater than or equal to the radii, we want to return false. So the distance between the circles, the center of the circles, is greater than the radii. And what that looks like, let me go ahead and draw that here. So we have a circle here and a circle here, and then each one has a radius that looks like this. So what we're basically saying is if this distance here, d, is greater than these two added together, then it's not intersecting. We don't have intersection, we can just return. And it's giving me an error here because I need to specify some default values for out parameters. So I'm just gonna make the normal 0 and then the depth 0. Now if the distance is less than the radii added together, then we have intersection and we need to get the normal. And the normal is subtracting A from B. Okay, and that'll give us the direction. So you subtract the center of one from the center of the other, and that'll give us the direction we want to resolve the collision. So if I do A minus B, that means we're going to get a vector pointing from center B to A. And actually, what I want to do, I'd like our collision detection to take whatever the second object is and push it out of the first one. So I need a vector pointing from A to B. So the way that would look is B minus A, okay? And so that'll give us a vector pointing from A to B and tell us which direction we need to push B to be out of intersection with A. I also want this vector to just have a direction. I don't want it to have, I want it to have a magnitude of 1. All right, so we need, once again, we need to call our flat library for math. And I want to normalize this value, okay? So it's only going to be direction is what we're looking at with this normal. And then the depth is just going to be, okay, so we know the distance is less than the radii. So the depth is just going to be the radii, or it's the these two, the radius of A and B added together, and then we subtract the distance between them, okay? And that'll give us how much depth we need to move apart. And then at this point, there was a collision, so we're going to return true and just indicate that that is it. All right, so now back in our game class, that should be everything we need to resolve the collision of the circles, I think. So let's just go back to the game and let's test it out, see if it worked. We have a list of 10 bodies, and I am inside the update function here. And down at the bottom here, what we're doing is we're moving, we're going to do all of the movement. And our physics engine is going to work this way as well. So we're going to do all of the movement, and then we're going to check for overlap, and then we're going to resolve the collisions, and then we're going to apply impulses to make them move in different directions depending on how the collision happened. So it's going to be a lot. This is basically the same direction our physics engine is going to go as well. But we need to loop through all of the entities. And so I'm going to make a for loop that loops through the body list. And then we need to loop through every other body in the for loop and compare them for intersection. So it's a double for loop. And this is what they call this is basically a brute force collision detection. This is brute force, meaning we're just looping through every body, comparing it to every other body, and checking if we need to resolve the collision or checking for collision and then moving them apart. Now, later on in the physics engine, we are going to make a better way of handling this so we don't compare every object to every other object, only the ones that are closer to each other. But for now, this is a good start just for getting things going. And the other thing is we can actually optimize the brute force method just a little bit. Now, one way to do it is we can just loop through every object and go through every other object. And then we just test if I is equal to j, then we continue, because we don't want to compare objects that are the same. But this for loop, what happens is we end up testing objects twice a lot of times. And we want some nested for loops that actually only compare the objects one time. And then we don't even have to do this check right here, because the way the loops are written, we don't even have to do this check. And in my flat library, I have a video in there for how to optimize these for loops or why we're writing it this way, which goes into more detail. And I'll put a link in the description for that as well. But the way it looks is for the top for loop, we start at 0, and then we loop to the count -1. And in the second for loop, we start at whatever I plus 1 is, and then we loop all the way to the count, just like that. And it's a very simple change, but it makes it so this loop only compares each object one time. They never compare one object to itself. So great way of setting it up. It also decreases the amount of loops you do as well. That's what that looks like. So in the first for loop, we're going to get a flat body. I'm going to call this body A, and that'll just be the body list at index I. And then in the second for loop, we're going to get another flat body, and that'll be body B, and that'll be at index J. So we have two bodies, and now we can start comparing them. Let's go ahead and do our check. So we're going to bring in the collisions. There we are, the collisions class, and we have the intersect circles. We need the center of A and the radius of A. So that'll just be body A position. And then the radius will just be body A radius. Okay, and we'll do the same thing for B. Okay, so if there is a collision, it's going to now pass out the normal and the depth. I'm going to change the lines I'm writing these on so they're easier to read. Okay, so we need to pass out a vector that has the normal of the collision and then a floating point that has the depth of the collision, and that should be everything. Okay, so now we know if they've intersected, and if they've intersected, all we want to do is push them apart by that amount, and we can use these values to push them apart. Let's go ahead and so for body A, we're going to move by a certain amount, and then body B, we're going to move by an opposite amount. And the way I set this up, so the normal will tell us the direction and the depth will tell us the distance. And so if we multiply those two values together, we're going to get a vector that will tell us how to, which direction and amount to pull them apart. So all we have to do here is pass in the normal and multiply it by the depth, and then the normal and multiply it by the depth. So there's actually just a little bit more we have to do here. So with the depth, what I want is I want each body to take half of the amount to resolve the collision. Okay, so if one body takes the full amount of the resolution, then one body will sit still and the other one will move all the way out. But I want each body to move just a little bit to correct for the depth or for the intersection. And so I'm just going to tell each one to take half of that amount. So I'm dividing the depth by 2, and that basically says you take half of the resolution and you take half of the resolution. And then also, if you remember what we're returning here with the normal tells us this is the direction I want you to move B to be out of a collision, right? So the B version will work, right? But if I want the opposite direction to move A, because I want to pull them apart in opposite directions. And so I'm just going to tell A that I want a negative normal, but I want to move it by the same depth. And so I think with that, we are all ready to go. And if I run this, we should be able to now move our circle around, and they should be colliding. So here's our circle, and you can see we are colliding perfectly. There we go. That looks really good. And let's see, it should work even with multiple collisions. So if I push this one over towards the other one, like this, you can see they're pushing each other away and resolving all of the collisions. And I can go in between them and push them out like this. That is so cool. I love it. Looks great. Looks really good. In fact, let's get a bunch of them lined up here. It's kind of hard. You got to get them lined up perfectly. So if I push this one down here, push this one over here, see if I can push all of these at the same time. Yeah, it's kind of hard to get them pushed like that, but perfect. It looks really good. So that is circle collision detection, and that's the basic collision detection for our physics engine. Again, we're going to start moving into things like boxes and rectangles using the separating axis theorem. And technically for circles, we did use the separating axis theorem to resolve this collision. It's just there's only one axis for circle. When you do circle to circle collision, there's only one axis. So that's circle collision detection and basic resolution.